Hello, everybody. Hope you're having a good morning, afternoon, or evening. Finally getting around to recording lecture 11. This is going to talk about radiation interactions with matter. So we talked a lot last time about the probabilities, the probability that a neutron would interact with a uranium atom, depending on its energy. We were very vague about it. We just said that there's some probability. Today we're going to start getting into the actual application of theory and prediction of that probability of radiation interacting with matter. First off, I wanted to share a thought. This is one of my favorite scriptures, actually, from no, not Doctrine and Covenants. This is from the Book of Mormon. I don't know why that says Doctrine and Covenants. Apparently I can't think straight tonight. Anyways, that's Book of Mormon. That's Alma, chapter 27, 17 through 18. It says, "Now the joy of Ammon was so great, even that he was full. Yea, he was swallowed up in the joy of his God, even to the exhausting of his strength. And he fell again to the earth. Now was this not exceeding joy? Behold, this is joy which none receiveth, save it be the truly penitent and humble seeker of happiness." Why do I like this scripture? For a couple reasons. One, it shows that the end result of being faithful to and following God is joy. But the second is this last little sentence here that's almost overlooked by many people. That this kind of joy, this exceedingly great joy, is only found by the penitent and humble seeker of happiness. While it's true that joy or that entertainment or temporary pleasure might fall upon us, it turns out that to find real happiness, we have to be looking for it. And one of these times when we're sitting in class, I'll tell you a story about this. So remind me about that. But for now, let's move on and start talking about radiation interactions with matter. So the one thing that a lot of people don't recognize, but it's crucial for us to understand in this course, is that the entire world is awash with radiation. There is so much radiation passing through everything. We have solar radiation, we have radiation from the ground, we have gamma radiation, we have all kinds of radiation that's constantly passing through. It is impossible for a person to have a zero dose of radiation. But there are some types of radiation that are more reactive or more problematic or more harmful for our bodies or for other forms of matter than others. There's some matter that very readily interacts with radiation, and there's some matter that does not readily interact with radiation. So what we need to talk about is taking the first few steps to understanding the impact of radiation and also knowing how it'll interact with different types of matter. So the first thing is that there are different particles and they have different effects. We've talked a little bit about this before, but now we're going to really emphasize it. So first of all, there's the alpha particle. That's like the helium nucleus. There's 2 protons and 2 neutrons, and that can be stopped by a sheet of paper. Why? Because it's literally a positively charged particle. There's no electrons around this nucleus, and so it very quickly wants to stop itself by attracting the electrons and absorbing that energy of its kinetic energy is stopped as you start to bind electrons. Also, it's a very large particle, so it's harder for it to pass through things. We talked about beta particles, which are essentially electrons. Those can be stopped by construction materials, a sheet of aluminum or plywood. Gammas are a lot more problematic. Since they're electromagnetic radiation or waves, they will pass through a lot of things. Typically, it takes several inches to feet of lead in order to stop them. And then we talked last time a little bit about neutrons. Remember we talked about how neutrons are constantly colliding with other nuclei, and they have kind of a zigzag pattern as they're scattered off these nuclei, and so the neutrons actually scatter around in a medium, bouncing off nuclei until they're absorbed. So what we're going to try and do now is we're going to derive a general term to try and quantify these interactions. Okay, so let's take a situation where we have a big chunk of a homogeneous material. Let's say some large block of iron. The probability that a neutron will interact is constant per differential unit of distance traveled. What that means is every distance unit, we'll call it delta x right here, that this particle travels through, there is a constant probability across that delta x that it will interact. Okay, this is something that's true for a homogeneous material. And what we want to do is we take the limit of this probability of interaction as that slice of x, or that length, decreases to 0. And that is this little variable that's represented by mu sub I. We'll talk about what that means. This is called the interaction coefficient. Okay, it's empirically derived. It's the macroscopic interaction coefficient, or in other words, it's the probability that a piece of radiation or a particle or wave will interact with a piece of matter in a specific zero length. Okay, so for all types of radiation except photons, we indicate this macroscopic interaction coefficient by capital sigma sub I. What does the sub I represent? Well, we use the I to connote what kind of interaction. We'll talk about that more a little bit later, but this is probably the most important thing for you to know in this lesson / prior to the exam. That is that this macroscopic interaction coefficient is the probability per length that radiation will interact with matter that it is passing through. So what does this cross-section depend on? It depends on the energy of the particle. Remember, as we've gone through the Q equations and the kinematic equations, the probability of interaction, or whether or not that particle will interact, depends on the particle energy, how fast it's moving. Okay, it also depends on the type of radiation. It also depends on the reaction type. Whether you have a scattering reaction or an absorption reaction or a fission reaction, if you'll remember, thinking back to the decay charts, remember how there were the different pathways decaying from that parent nucleus, and each pathway had a different frequency? Well, that frequency of interaction, like for decays, is true for two-particle interactions, except in this case there's some probability of scattering, some probability of absorption, some probability of fission, and if you add up those probabilities or those cross-sections, you will end up getting a total cross-section or total macroscopic interaction coefficient. So let me be clear here. I just mentioned the word cross-section. I don't think I introduced it before. So let me say macroscopic interaction coefficient connoted by sigma. When you're talking about neutrons, that's known as a cross-section. Okay? A macroscopic interaction coefficient is the same as a macroscopic cross-section. It's just, for one, we use the term macroscopic cross-section when we're talking about neutrons typically, and we use the macroscopic interaction coefficient when we're talking about other radiation, but it's all connoted by this capital sigma. So anyways, if you add up all of these macroscopic interaction coefficients for specific reactions, you'll get the total interaction coefficient. Okay, this interaction coefficient is also energy dependent. Okay, it's also known as the linear fission coefficient, the linear scattering coefficient, etc., depending on what the subset I is. So typically, this macroscopic cross-section, if it's sigma S, we know that it represents the macroscopic interaction coefficient or macroscopic cross-section for scattering. If this is sigma A, we know it's the macroscopic absorption coefficient. Okay? And this also depends on, so we talked about how the sigma, or the macroscopic interaction coefficient, depends on the particle energy, depends on the reaction type, and it depends on the medium type, or the type of matter that this radiation is passing through. So there's 3 degrees of freedom to this coefficient known as the macroscopic interaction coefficient, or the macroscopic cross-section. Okay? As I mentioned before, these things are linear. So the total scattering coefficient, sigma t, is equal to all of the constituent reaction coefficients. Okay? So we have the linear scattering coefficient, we have the non-linear scattering coefficients that we add together, we have the total absorption coefficient, sigma a, we have the neutron, which is comprised of the neutron capture coefficient, sigma c, the fission coefficient, sigma f, and other neutron absorbing interactions. Okay? So what does this mean? That means the probability of any interaction per unit differential path length is the sum of all the individual interaction coefficients. So if we take the macroscopic interaction coefficient for total scattering, for total absorption, which is composed in turn of all these individual parts, and add them together, that will give us the total macroscopic interaction coefficient for the material. That again represents the probability of any interaction per differential path length. So what are the units of the cross-section? It's going to be per length. Okay? So If we're talking about photons, again, specifically to photons, this is called the linear attenuation coefficient, or more specifically, the linear interaction coefficient. Okay, again, this is a function of energy, and it's simply the sum of all the individual parts of the macroscopic interaction coefficients. Okay, so the way that we have thought about this and derived this is we do a little thought experiment where we imagine some beam of radiation that's interacting with a slice of material with thickness delta x. So we have intensity of that beam, or I, as a function of x coming in, and as it passes through this material, it comes out with a different value. In other words, some of that radiation in the beam of intensity I actually interacts with the matter and no longer passes straight through. It's scattered in a different direction or absorbed, and what comes through is the remaining intensity of the beam. And so now that's the intensity of x plus delta x, which is a different value than the intensity at x. Okay, and you can see here, this is a depiction of the decreasing intensity of the radiation. In other words, the number of particles per second as you go through this material. Okay, so the probability of interaction, or P of x, is essentially the intensity going in minus the intensity going out divided by the total intensity. In other words, if you see here, those are the particles that did not make it through this medium. What's going in minus what's going out is the amount that didn't make it through. So the amount that didn't make it through divided by the total amount is a fraction that represents the probability of interaction across delta x. Okay? So that considered, the linear attenuation coefficient, or the macroscopic interaction coefficient, is equal to the probability of interaction across delta x over delta x as the limit of that quantity as delta x goes to 0. Okay, that's also equal to the limit as x goes to 0. The limit as delta x goes to 0 of intensity at x minus the intensity of x plus delta x over delta x times I of x. That's simply substituting this quantity for probability with this definition for the probability. Okay? Then when we take that limit, it turns out that this is equal to 1 over the intensity of x times di dx. Okay? In other words, this is just the derivative of the intensity with respect to x. Okay? Multiplied by 1 over the intensity. That's all this is. So in other words, di dx, or the differential change in intensity per unit length, is equal to the negative linear attenuation coefficient, or macroscopic interaction coefficient, times the intensity at x. Or in other words, the intensity at x is equal to the intensity at 0 times e to the minus mu sub I x. So again, where mu sub I is the attenuation coefficient, which is dependent upon the type of radiation, the energy, and the specific material that it is passing through. Okay, so you'll notice there's 3 different terms for this. If you're dealing with photons, this term is called the linear attenuation coefficient. If you're dealing with other types of radiation, this is known as the macroscopic interaction coefficient. If you're dealing with neutronics, which is how we're primarily going to use this, this is known as the macroscopic cross-section. It all means the same thing. It relates to the probability that a particle will interact with a type of medium per unit length of that medium. Okay? Again, the units per length. It's all the same thing. We call it 3 different things for 3 different classifications of radiation. It's horribly confusing. Nonetheless, that's how we've decided to deal with it in nuclear science. So primarily what I'm going to focus on, and what I'm going to try to call it from here on out, because of our focus on neutronics, I'm going to try and call it the cross-section, except for the few slides where I'm going to be talking about the linear attenuation coefficient for photons. Okay? So again, the interaction probability in distance x is going to be equal to 1 minus the intensity at x divided by the initial intensity before you pass through a material, or in other words, 1 minus e to the minus cross-section of I times x. So therefore, the probability that a particle does not interact in distance x is going to be, we're going to call that p bar, that's going to be 1 minus probability of x. In other words, if the probability of interaction is p, the probability that it doesn't interact is 1 minus p, which is simply 1 minus the ratio of the intensities, or e to the minus cross-section times x. Okay? Therefore, we can use that to figure out the average penetration distance until an interaction, or the mean free path length. When we talk about radiation, we're going to talk about the mean free path length. That's how far, on average, that particle of radiation or that wave of radiation will go without having an interaction. As an example, let's think through this. What is the mean free path of a neutrino? Several million kilometers at times, okay? Because neutrinos do not readily react with baryonic matter. How about the mean free path length of an alpha particle? Millimeters, if not micrometers, if passing through a medium, okay? So the average penetration distance until interaction, or the mean free path length of a particle, can be discovered from these probabilities by integrating from 0 to infinity the length times the probability of interaction at that length, okay? In other words, if we break this up into the two pieces, we have the probability that the particle will get to point x, and then we have multiply that by the probability that it will then interact in the next dx, or slice of length. Okay, so in other words, this is the probability that the particle even gets to that length, that distance in the first place, and this is the probability that it then interacts in the very next piece of dx. When we multiply that by x and integrate from 0 to x, that gives us the mean free path, or the mean distance that that particle will travel before it has an interaction. And that's equal to this exponential, because of what we know for the definitions of p bar and p as given above. Or in other words, u sub I over u sub I squared, or 1 over u sub I. So the mean free path, or the length that a particle will travel before interaction, is typically 1 divided by this macroscopic cross-section or attenuation length, which is the probability that it will interact per length. So that makes sense. This is the length per interaction, or the inverse of the mean free path, which is the probability of interaction per length. Okay? So how do we think about this conceptually, now that we've kind of showed you the math that we went through to derive this? So it can be thought of in three ways. First of all, it's the probability that a particle interacts in a differential length of material. So when we talk about fissions, and we talked about the probability of fission and how low energy neutrons are more likely to cause a fission than high energy neutrons, what that means is that uranium-235 has a high cross-section for low energy neutrons and a low cross-section for high energy neutrons. Okay. Another way we can think about it, part two that we can think about, is that it's the inverse of the mean free path of a particle. Or in other words, the path a particle will travel through a medium or through a homogeneous material before it interacts. So the inverse of that, or the length, or the probability of interaction per length, is equal to that cross-section, or that linear attenuation coefficient. Okay. And the third way that we can think about it for, because it's the average mean free path, or the average distance that a particle will travel before interaction, we can also think of this as the distance at which half of the particles in a beam or a flux have interacted. Okay, in other words, you can see here the length at which half of the particles have interacted, which is analogous to the time at which half of a material has decayed. So it's analogous to the half-life. It's this halfway distance where half the particles have interacted. That's equal to the natural log of 2 over that interaction coefficient. So very analogous to half-life, except instead of using time, we're using distance, the distance traveled. So these are the three ways that you can think about this linear attenuation coefficient, or macroscopic cross-section. Okay? This, as I mentioned, is somewhat analogous to decay constants, right? Where we talk about, with decay constants, we talk about decay probabilities. We can't say exactly when a particle will decay, but we can say, on average, how long it takes until that's decayed, or the average lifetime of the particle. Again, that's why you see this analogous representation between distance between interactions that looks a lot like half-life. Okay? So in many cases, interactions don't eliminate the particles. We talked about neutrons scattering off of hydrogen this morning and talked about how that interaction does not eliminate the neutron. The neutron's not eliminated until it's absorbed. And so there are several, in fact, many nuclear interactions where you simply scatter the particle. Okay? And so what's important to know here is the total number of particles. This is very, very complex. We want to know the total number of particles because if we know the total number of particles, we know with each probability of interaction exactly when and where and how these interactions will occur. We'll know how many interactions will occur, and therefore we will know how many fissions are occurring per second. And therefore we'll know how much power is generated per second. So it's important for us to know the total number of particles in a medium, or what we call a radiation flux. Flux is simply, as if you'll remember from fluids or from heat transfer, it's the transfer of some material through a distance per area per time. Okay, in other words, it's like a velocity or amount passing through an area per time. And so a flux of radiation is the amount of radiation passing through a cross-sectional area per time. Or in other words, particles per centimeter squared per second. Okay, this sounds simple to know how many particles are there, but it is horribly and hugely complicated with a lot of computations involved. Why? Because you have some particles that instead of being absorbed are scattered, and you have to keep track of every single one of those particles. And we're talking about quadrillions, if not quintillions or sextillions of particles. Then on top of that, you've got to keep track of their energies, which ones are getting absorbed, which ones are not getting absorbed, the formation of new particles, and so on and so forth. This is basics of what we call the field of neutronics, keeping track of and tracking the movement of neutrons in particular, but also you can do this type of analysis with other forms of radiation. There's a very not sophisticated, but a very well-known and proven code called MCNP, Monte Carlo Neutron Proton. The whole point of this code is it goes through a stochastic series of calculations to try and evaluate the total number of particles and the total interactions that are occurring for radiation. However, when you develop complex geometries and you have neutrons passing between different materials with different cross-sections and different energies for each, it generally will take an entire quarter of a year to evaluate a small slice of time for a full nuclear core. So they're very complicated and very calculated, or very complex calculations. So what we'll typically do in order to figure out the total number of particles, rather than our example, you remember our example, let me back up a few slides. We showed this example where we had a radiation beam of intensity I passing through a medium, and we wanted to figure out how many particles came out the other side. That doesn't tell us how many particles are actually there, because some of these radiation particles didn't get absorbed. They just scattered in a different direction. They're still there. They're still part of the medium. They're still passing through that medium. So for us to say that this I of x plus delta x is the total intensity is wrong. It's just the intensity in that one direction. Okay? So there's a directional component to that. So what we do is we derive what we call a buildup factor that correlates the complex calculations here with a very simple expression, and that is the intensity at x that's not directionally dependent. So the total intensity at x is simply equal to this buildup factor times I times e to the minus macroscopic cross-section or linear attenuation coefficient times x. What does this mean? Okay, let's break this down. The intensity at any given point x is equal to the initial intensity times this attenuation factor. In other words, this term here combined with this term here indicate the or the intensity of the beam going in the same direction. That's exactly what we derived on this slide here, that the intensity at any given point is equal to the initial intensity times the amount that relates to the decay or how much has interacted. Okay, but since that amount of particles or that intensity hasn't accounted for the scattering or the particles going in different directions, we need to account for that with this fudge factor b. This is typically very common in calculating doses. Rather than trying to calculate the total particles moving in all directions, we just figure out the linear attenuation, or the amount that moves linearly through the medium, and then we multiply it by this complex buildup factor. And this is what's calculated through very complex calculations. And then what happens is we use that to evaluate how much total flux there is based on the linear propagation of the flux. Okay? So now let's talk about what we call the microscopic cross-section. The probability of interaction, as we mentioned before, is proportional to the number of atoms. In other words, if you have a stream of neutrons passing through a tiny cube of uranium, you're going to have some number of interactions, right? Because there's a certain number of neutrons, there's a certain number of nuclei. However, if we increase that tiny cube to a huge, massive meter squared or a meter cubed chunk of uranium, which by the way isn't possible because it would blow up like a bomb long before that. But if we were to increase that to a meter cubed section of uranium, there'd be a lot more interactions because there's more uranium around. Okay, so the probability that radiation will interact is proportional to the concentration of atoms. Or in other words, this macroscopic cross-section is equal to a smaller non-amount dependent cross-section that we call the microscopic cross-section times the number of atoms per cubic centimeter, or the number density. Okay, so let's take a step back. This is probably the most important thing for you to know from this lecture. Okay, that the microscopic cross-section is defined per element, per reaction. So as an example, we talked about uranium. Uranium has a specific microscopic cross-section for fission. It's known as sigma F. That cross-section is the same no matter how much uranium-235 you have, but it is unique to uranium-235. Every element has a different cross-section for each interaction. Then, in order to get the total probability of interaction per unit length, we multiply it by the total number of uranium atoms. In other words, this is the probability that a particle will interact with an atom, and this is the total number of atoms. That gives us, if you multiply out the units, probability per length times the number of atoms per cubic centimeter. That gives you the macroscopic cross-section, or the linear attenuation coefficient. Okay, so in order to figure out the number density, if you remember from the first chapter, it's simply going to be the density of the material times Avogadro's number divided by the atomic mass of the medium. Okay, so those are all synonymous and equal. This is probably one of the most important concepts for you to know. I guarantee you will see quizzes, tests, etc., where you will need to know what the macroscopic cross-section is, what the microscopic cross-section is, and how to convert between them. Why? Well, because the microscopic cross-section is given in tables, in books, in charts for every element, for every energy, and for every type of particle. You don't have a table full of the macroscopic cross-sections because it depends on how much material you have. So if you know how to look up and use the microscopic cross-section for fission, for absorption, for the totals, and if you can multiply that by the number density, which you can evaluate here, you can figure out the probability that radiation will interact with that matter per unit length. And that is of vital importance because we can use that directly to figure out the number of reactions that are occurring per time. And we'll talk about how to do that. But for now, please, please, please know, memorize, and be able to work with this exact equation. It is of vital importance for everything we do moving forward, both nuclear reactor core interactions as well as interactions for detection, and finally for health physics and just standard radiation absorption. Okay? So again, probably the most important things for you to know and recognize from this lecture is that the macroscopic cross-section is the probability of interaction per unit length, whereas the microscopic cross-section is equal to the probability of interaction for a specific reaction and material and energy. Okay, and if we multiply that by the number of atoms, that gives us the total probability. So the probability of interacting with a single atom times the number of atoms gives you the total probability of interaction per length. Okay, so the macroscopic cross-section, I'm sorry, the microscopic cross-section, as I just said, is independent of the amount of material you have. Okay? It's strongly based on the particle kinetic energy. So in other words, if you have a neutron coming in at 10 MeV, it's going to have a totally different cross-section than a neutron coming in at 1.5 MeV. What does this mean? Oftentimes for cross-sections, rather than given just a single value, you'll be given a plot of what cross-section is as a function of incoming particle energy. And you'll have a different plot for every single element, or isotope even. Okay? So this takes into account the three dependencies. Remember, the probability of interaction depends on energy of the incoming particle, the type of the incoming particle, and the element that it is passing through. Okay? And there's no way for us to predict this. This is quantum mechanically based. We cannot look at an element and say the probability of interaction is this. So how do we know these microscopic cross-sections? How do we get these tables full of charts and numbers to show whether or not a particle would interact? They're empirically derived. There were millions upon millions of experiments that have been performed at every possible energy, every possible isotope, every possible incoming particle of radiation to determine vast tables of cross-section data. What that means for us is we can go and evaluate that. If you remember the first day of class, I gave you a table of a link on the website indicating it's called the NDEF-B cross-sections, that gives you the cross-section for neutrons in particular across a wide range of energy for a huge number of isotopes. And that's vitally important, and I'll show you some plots, some examples in a little bit. What are the units for these cross-sections? Remember, we're dealing with very, very, very small particles. The typical unit is called a barn. Why in the world is it called a barn? It's because the smart aleck nuclear physicist that came up with this concept said, after somebody brought up the size, well, that's as big as a barn, and the name stuck. So unfortunately, we now call barns, that's equal to 1 times 10 to the minus 24th centimeter squared. Okay, this is kind of an interesting unit, isn't it? It looks like an area. It looks like we're talking about the cross-sectional area of an atom. In fact, we call it the cross-sectional area. That's a funky name. Just be aware that it isn't really an area. Remember, we're dealing with quantum mechanical interactions between the neutron and the nucleus. However, when we treat it classically, we can pretend and approximate this as if this cross-section or probability of interaction were an area. Therefore, the larger the area, the more likely it is that the particle will interact with that nucleus. Please remember, that's not actually what this represents, but it is representative of that. Okay, we're talking about a classical interaction to represent the probability of interaction. Okay, so you're going to have these microscopic cross-sections listed in terms of barns, and each barn is 1 times 10 to the minus 24th centimeter squared. Okay, so one barn is the approximate physical cross-section of a uranium nucleus. Okay. Now, we talked about how photons have different terminology. They actually have a different mode of interaction and different calculations than everything else. We deal with the mass interaction coefficient. And typically what we'll do, because it's dependent upon a specific material, just like for other forms of radiation with the cross-section here, we will have an interaction coefficient divided by the density, and these are the values that are tabulated. So you'll actually have this interaction coefficient divided by the density that will be tabulated. And it's actually weakly dependent on the properties of the medium for photons only. Okay? So in other words, this interaction coefficient divided by the density, which is the same thing as the cross-section of the photons interacting in the medium times the number density of the medium divided by density, is equal to this Avogadro's number over A times the cross-section. But again, for photons only, typically you'll have this quantity listed in tables. And in fact, in the back of the book, you'll see several quantities listing the photon interaction coefficients as mu sub I over rho, where I is replaced with scattering or absorption, etc. Okay? So if we have a mixture, how do we deal with the cross-section? What we do then is we treat it, if it's a homogeneous mixture, as a summation. Okay? So in other words, the total cross-section is going to be equal to the sum of all the individual mixed cross-sections. But keep in mind, these macroscopic cross-sections are amount dependent. So in other words, the total macroscopic cross-section of some medium is equal to the sum of each individual microscopic cross-section, sigma I, for that reaction times the number of atoms, for that element or isotope times the number of atoms of that element or isotope. So all you're doing is getting the macroscopic cross-section of each interaction. Remember, the microscopic cross-section times the number density gives you the macroscopic cross-section. So this total macroscopic cross-section is just the sum of each individual part times the total. Okay? And the same thing is true for the linear interaction coefficient or the photon parallel, and that is, it's simply going to be the mass fraction times the linear attenuation coefficient summed up for all the individual parts. So if you're trying to figure out the cross-section for water, the scattering cross-section for water is simply going to be the microscopic cross-section of oxygen times the number of oxygen atoms plus the microscopic cross-section for hydrogen times the total number of hydrogen atoms. And that will give you the total cross-section for water. That's it. Okay, so you can linearly add up the pieces across different cross-sections to get the total, and also across different number densities to get the mixture cross-sections. Okay, so another way you can think about this when we're talking about this radiation beam that I mentioned before, the total collisions are equal to the cross-section times the intensity times the number of nuclei in the target. In other words, the number density times the area times the thickness. Okay, so the total number of collisions of radiation per second is simply going to be the cross-section, or the probability of that interaction, which is units of Barnes, or centimeter squared, okay, times the beam intensity, which is going to be the particles per second, and that's going to be multiplied times the number density times the area times the thickness. Okay, so the collisions per second with a single nucleus times the total number of nuclei will give you the total collisions per second. This is very important. It's simple, but it's very important to know, because if you ever want to know, for example, how much radiation is passing through a designed shield, you need to know the type of material and the energy of the neutrons. That gives you sigma. You'll need to know how many neutrons are hitting that shield. And if you want to do all directions, you'll have that B factor. And then you'll need to know how many nuclei are in that path of the radiation to give you the total collisions per second. Okay? I mentioned this before. This is just to reiterate. The cross-sections for each interaction can be summed to give you the total. So this is sigma t, or the total microscopic cross-section, is equal to each individual component. The fission, the capture or the gamma release, right? And the other interactions all can be added together. So in other words, the absorption cross, this is, by the way, the elastic scattering, this is the inelastic scattering, this is the radiative capture, this is the fission. So if you're looking at the total absorption cross-section, that's going to be equal to the total radiative capture plus the fission. Remember, I mentioned fission was a special form of absorption, plus the alpha particle release, in other words, where it absorbs the particle and releases an alpha, plus the proton particle release, where it absorbs a particle and releases a proton. Adding all those together gives you the total absorption cross-section. Likewise, if you want the total scattering cross-section, it's going to be the elastic plus the inelastic scattering coefficients. Finally, the total cross-section can be determined from the total cross-section is equal to the scattering cross-section plus the absorption cross-section. Those are really the only two things that radiation will do when it hits a nucleus. It will either scatter or it will be absorbed. Okay? Now keep in mind, the absorption is divided into all these subsets of gamma release, fission, alpha, proton release, whereas the scattering can be divided into the elastic, inelastic scattering, etc. So this is very important for you to understand, that the microscopic cross-sections, not the macroscopic, but the microscopic cross-sections that are material dependent only, are additive. So if I were to give you a type of problem where I said the scattering cross-section of hydrogen is X barns, and the inelastic scattering is Y barns. Tell me what the elastic scattering coefficient is, or you could say, tell me the number of particles that interact in an elastic scattering reaction. You would find that by subtracting the total scattering from the total scattering cross-section, the inelastic scattering cross-section. Okay? So what's the significance? We talked about the intensity of a beam at point X. This is the uncollided intensity, meaning we're not taking into account that B factor. That's going to be dependent upon the exponent of the macroscopic cross-section times the length. Okay? That's also equal to the microscopic cross-section times n. Remember, the macroscopic is the microscopic times n, the number density of the atoms. So that total uncollided flux at any point X is going to be equal to the initial uncollided flux times the exponent of the macroscopic cross-section, which we break down into the number density times sigma times the density divided by the atomic weight times X, or the thickness of what it's passing through. Okay? Key to remember, macroscopic cross-section is equal to the microscopic cross-section times Avogadro's number times the density divided by A. Okay? So for photons, similarly, you're going to have all kinds of interactions that occur by the photons. We talked before about Compton scattering of the photons, where you have the photon causing a scattering of the electron, that interaction between mass and particles. You'll have annihilation photons, you'll have fluorescent photons, you'll have Brechtelung, all these different kind of interactions that occur at different energies. All of these mechanisms cause a photon to lose energy, just like any other particle, but the ones that are listed here mostly deposits energy elsewhere rather than locally. In other words, it will cause a particle like an electron to shoot off, and then that electron will slow down and deposit its energy elsewhere. Okay? So we've already talked a little bit about the linear coefficient. I'll leave you guys to look at this if you're interested. But this is generally the linear coefficient for photons. Remember, it's the same concept as the cross-section, but it's specific to photon interactions. Okay? So let's again just remind us all of when classical evaluation is acceptable. Hopefully you remember this, but I want to iterate it one more time. By the way, if I iterate things multiple times, there's a very good probability you're going to want to know it. If you're at low particle speeds or low particle energy, then typically you can use classical evaluations. However, you will need to use relativistic evaluation if you have high particle speeds relative to the mass energy. Okay? This is analogous to cross-sections as well. Okay? So we have the physical cross-section is dominant for low energy scattering, but you have the radiative absorption dominant. The term is dominant when you have high energies. Okay? So let's talk about cross-sections really quick. We're just about finished here. Most isotopes, the cross-sections increase as the neutron energy decreases. In other words, as the neutron has more energy, the total cross-section, as the neutron has more energy, the total cross-section will actually decrease. We talked about this for uranium. In other words, the higher the energy of the incoming neutron, the lower the probability of interaction. That's because the cross-section decreases as neutron energy increases. This is true for most isotopes. Now, there's an interesting phenomenon that we see as the neutron slows down. As that neutron starts to slow down, in the cross-section plot, we see resonance regions where we see all kinds of narrow spikes and valleys. And these resonance regions have rapidly varying interactions, cross-sections, that really aren't solvable analytically. They're not resolvable, okay? And so that becomes an area where the probability of a neutron being absorbed really increases. And we'll talk about that. That's important when we talk about the design of nuclear fuel. But anyways, when we talk about light versus heavy isotopes, just a generic rule of thumb, when we talk about light isotopes, we're typically talking about isotopes with an atomic mass less than 25. When we talk about heavy isotopes, we're talking about isotopes with an atomic mass greater than 150, and intermediate is in between. So I promised some examples. I want to show you here, this is an example of a cross-section plot for a neutron. Okay? In other words, this is for some material, the probability that a neutron will interact in barns. Remember, that is the unit of the microscopic cross-section. The probability that the neutron will interact in barns as a function of energy. And you'll notice this is in MeV, so this is very small energies, very reasonably high cross-section. We're talking about 1175, almost 1200 barns. I'm sorry, 11.75, almost 12 barns. However, as we increase the neutron energy, that cross-section decreases. So the faster the neutrons, the less likely that it will interact with the isotope. This is why we need to slow neutrons down to cause effective fissions. As we continue to increase the energy, suddenly we get to this point where you have sudden narrow peaks or increases in cross-section. You see that? As we're increasing neutron energy, we have all these peaks. These are what we call the resonance region. It's very probable that a neutron will be absorbed if it's hitting matter during this resonance region, because you can see there's sudden increases in the probability of absorption. Okay? We call this the resonance region. As you continue to I'm sorry. This is for aluminum, and then I included one for iron so you could see the difference. Iron has a significantly higher neutron cross-section at the same energies. This goes up to it goes up to about 225 almost, it looks like, barns. That's significantly higher than aluminum. It was about 12 barns. So for iron, the cross-section, the total cross-section is about 225-ish, and it decreases as you increase the energy. And then again, as you increase the energy further, you reach this resonance region where the probability of absorbing the neutron dramatically increases. Here is the total cross-section for lead. Notice that it's a little bit smaller than aluminum, but bigger than what you see for, it's a little bit smaller than iron, but bigger than aluminum. And again, you have this resonance region. So let's get to the plot that's the most important and significant and interesting for what we want to do. This is the plot of the fission cross-section for uranium-235. I want you to notice that if you go down to very slow neutrons, remember this is in MeV, so this is almost getting to that thermal region we talked about, that's 0.025 eV. Cross-section is almost 10,000 barns. It is a massive cross-section, and it decreases virtually linearly. 1 over V is what we refer to that as. That decreases almost linearly as the neutron energy increases. You can see why it's important for us to decrease the energy of the neutron. This is a log plot. So if you go from about an MeV to here, you're increasing by 100 times the probability that that neutron will cause a fission. This is why we slow them down using hydrogen. Again, note that this is a log scale, okay? And then once you go up a little bit higher in energy, you get the resonance region where you hover around 100 or more or less, okay? Again, the scale, we're talking about hundreds rather than here thousands and tens of thousands of barns. And this is the zoomed out resonance region, okay? And then once you get past the resonance region, you get to the smooth region, okay? This is where you don't have quite so much of those peaks and spikes. But you notice that now we're down to the single digits of the cross-section. This is the fast neutron spectrum. This is where they come out when they first are formed from a fission or where they're born. And we're trying to slow them across the resonance region until we get to this thermal or high fission cross-section region. Okay? That's why we do what we do with uranium-235, as explained by these cross-section plots. So again, this is cross-section as a function of energy for a specific material. Here it's 235, and this is the fission cross-section only. As we get past that resonance region, we get down into the lower areas for the fast, and then suddenly we have that bump up for the very fast neutrons where you have a reasonable, but still in the fraction of a barn section for the cross-section. Okay? So if we're to look at the total cross-section versus the fission cross-section over the entire energy range for uranium-235, this is what it looks like. If you have a fast neutron, you'll notice that the fission is a significantly smaller fraction of the total cross-section. But when we move into this thermal region, the lion's share, not only is the total amount bigger, but the fraction is significantly larger than it is fission. So we come to this region because the probability of inducing a fission rather than an absorption is incredibly high when you get to this thermal region as compared to this fast region. Okay. Meanwhile, if you look at uranium-238 as a function of energy, do you see this? The fission cross-section is almost zero when we're down here in the thermal region. In other words, as I mentioned in class, U-238 is not fissile in a thermal reactor. However, look what happens as we start to increase the energy. As the neutron energy increases, we begin to see that it becomes fissionable. Okay, it's not fully fissile because it's going to still have a relatively small cross-section, but we do get to see some of that U-238 have inducing fissions. Okay, so here's the fissionable cross-sections for several different materials. I think this is good for now. Once we get to this section, we're going to get to what we talk about Monday. We're going to start talking about the derivation of cross-sections. This is towards the end, but we'll go through that derivation later because it's already been kind of a long lecture. Hope it was understandable. We'll take some time Monday to ask any questions. Please watch this. There are a couple of crucial points, particularly the microscopic and macroscopic cross-sections and their related fraction that you guys are going to want to know for quizzes, for tests, for assignments, etc. Thanks again, guys. It's been great teaching you so far, and hopefully this continues, and we'll talk to you later. Bye.